1, 2, 3.
Today, I'm going to present Chapter 8, Mathematical Modeling. What is mathematical modeling? Mathematical modeling is the process of constructing mathematical models. In mathematical modeling, a real-world problem will be translated into a mathematical problem. We then solve the mathematical problem and interpret its solution in terms of the real-world problem. A mathematical model is a representation of a system or scenario that is used to gain qualitative or quantitative understanding of some real-world problems and to predict future behavior. Let us consider the following problems. Example question 1. The population of town A is 40,000. It is known that 45% of the residents in the town practice the habit of recycling used plastic drinking bottles. If each person in the town uses 5 plastic drinking bottles per week, how many bottles are recycled each week in the town? This is an example of a problem-solving question to reinforce the concept of percentage. The problem explicitly gives us all the information we need. We only need to determine the appropriate computations to arrive at one correct answer. Example question 2. How long does it take to clean up an oil spill in the ocean? It is an open-ended question. We usually do not have complete information when trying to solve real-world problems. These real-world problems demand us to use both mathematics knowledge and creativity to solve them. In this case, mathematical modeling is perfect for solving such open-ended questions. There are a few important components that involve in the mathematical modeling process. The modeling process can be simplified as shown in the diagram below to solve real-world problems. Number 1, identifying and defining the problems. Number 2, making assumptions and identifying the variables. Number 3, applying mathematics to solve problems. Number 4, verifying and interpreting solutions in the context of the problem. Number 5, refining the mathematical model. Repeat as needed. And the last step, reporting the findings. Now, let us look at one mathematical modeling example that involves all the above components. Example 1. The grocery store which is far from your house sells a pack of 10 kg rice at a lower price than the one closer to your house? Is it worth the drive for the cheaper deal? The first step, identifying and defining the problems. The price of a pack of 10 kg rice and the cost of petrol. Determine the distance from the two stores to your house respectively. Find the information needed from the internet. For example, the price of a pack of 10 kg rice from each store, the distance of each store from your house, the current petrol price, the car's petrol consumption rate, and so on. Step 2. Making assumptions. We can assume that the road between the house, store A and store B is a perfect straight line. We can also assume that we are driving car to the stores and purchasing the same number and brand of rice at store A and store B. Identifying the variables. Let S equals to the distance between store A and store B. P1 equals to the price of a pack of 10 kg rice at store A. P2 equals to the price of a pack of 10 kg rice at store B. M equals to the petrol consumption rate of the car in km per liter. N equals to the number of packs of 10 kg rice to be purchased. H equals to the current petrol price in Rm per liter. S equals to the difference in price in Rm for purchasing the pack of 10 kg rice at store B as compared to store A. T equals to the difference in the cost of petrol in Rm for driving to store B as compared to store A. The price of a pack of 10 kg rice at store A is 25 ringgit 95 cents and at store B is 23 ringgit 99 cents. Let the quantity of 10 kg rice to be purchased be 2 packs. So the price to be paid at store A is 51 ringgit 90 cents. At store B is 47 ringgit 98 cents. 51 ringgit 90 cents minus 47 ringgit 98 cents equals to 3 ringgit 92 cents. Therefore, by purchasing the rice at store B, one can save 3 ringgit 92 cents. Let the distance between store A and store B be 6 km. The petrol consumption rate of a car be approximately 17.6 km per liter. The current petrol price be 2 ringgit and 8 cents per liter. Petrol needed for 6 km road. 6 km over 17.6 km per liter equals to 0.341 liter. Cost of petrol for 12 km road. 0.341 liter times 2 ringgit and 8 cents per liter times 2 equals to 1 ringgit 42 cents. 3 ringgit 92 cents minus 1 ringgit 42 cents equals to 2 ringgit 50 cents. Therefore, we save 2 ringgit 50 cents by purchasing 2 packs of 10 kg rice at store B. Step number 4. Verifying and interpreting solutions in the context of the problem. The resulting mathematical model is as follows. S equals to P1 minus P2 times N. T equals to Sm times H times 2. If S is bigger than T, then it is sensible to drive to store B to purchase rice and save more money. If S is smaller or equal to T, then we should not drive to store B to purchase rice. Example of using the model. S equals to 25 ringgit 95 cents minus 23 ringgit 99 cents times 2 equals to 3 ringgit 92 cents. T equals to 6 over 17.6 times 2.8 times 2 equals to 1 ringgit 42 cents. Since S is bigger than T, you save more money by purchasing rice at store B. Hence, it is sensible to drive to store B. The mathematical model is able to solve the problem. When we are verifying and interpreting solution, we consider, are the solutions able to solve the problem, and it is rational to translate the solutions to real-world situations. From the constructed mathematical model, further exploration can be made. First, if all the variables remain the same, how far can store B be located so that it is an optimum choice? 25.95 minus 23.99 times 2 is bigger than S over 17.6 times 2.08 times 2. S is smaller than 16.6 km. This means that if the distance between the two stores is less than 16.6 km, then it is sensible to drive to store B to purchase rice. Number 2. What is the maximum price of a pack of 10 kg rice at store B that will attract a person drive to store B to purchase it? 25.95 minus P2 times 2 is bigger than 6 over 17.6 times 2.08 times 2. P2 is smaller than 25.24 ringgit. This means that if the price of a pack of 10 kg rice at store B is less than 25 ringgit 24 cent, then it is worth the trip. Step 5. Refining the mathematical model. The assumption made regarding the road between the house, store A and store B is a straight line needs to be revised. If the road between the three places is not a straight line, how does this impact our model? If new assumptions are being made, then the model needs to be revised to reflect this change. Step number 6. Reporting the findings. We can use symbols and diagrams when necessary to report the findings. Every model has strengths and weaknesses. What is important is that the model identifies those strengths and weaknesses in the report. For example, the value of a person's time is not considered in this model. Is it worth driving an extra 12 km for someone to save 2 ringgit 50 cents? According to this model, saving 5 cents is considered worthwhile. The model did not account for any environmental consideration. Is it environmentally responsible to drive an extra 12 km just to save 2 ringgit 50 cents? This model does not account for environmental effort, such as efforts to reduce carbon emission. Example 2. The diagram below shows the cross-section of a river. A hydrologist measures the depth of the river Ym at different distance xm from the river bank. The results obtained are given in the following table. The first step, identifying and defining the problem. How to determine the depth of the river? Second step, making assumptions and identifying the variables. We assume that the river is deepest in the middle, with the depth decreasing to 0 at the edges. The two variables involved in this study are the depth of the river, Ym, and the distance from the river bank, Xm. Step number 3, applying mathematics to solve problems. Write the distance from the river bank and the depth of the river as a set of order pairs X and Y, and draw a graph for the data. The data seem to rise and fall in a manner similar to the quadratic function. The graph drawn shows the curve of best fit and resembles the graph of a quadratic function. In mathematical model, to represent the actual situation, the approximate value is used. Based on the graph, the depth of the river is 3m when the distance from the river bank is 15m approximately. Substitute equation 3 into equation 1. 1.7 equals to 625a plus 25 times negative 38. A equals to negative 0.0136. Substitute A equals to negative 0.0136 into equation 3. B equals to 0.408. Hence, the possible quadratic function is y equals to negative 0.0136x squared plus 0.408x. Substitute x equals to 15, y equals to 3.06. Approximate to the answer obtained from the graph. Step 5. Refining the mathematical model. For this model, we assume that the river is the deepest in the middle. This may not be true for some other rivers. A new model will be needed if we have new assumptions. The answer will be more accurate if more data have been collected. The last step, reporting the findings. Write a full report following the above modeling framework structure. Example 3. Compound interest is interest that is calculated based on the original principal and also the accumulated interest from the previous period of savings. At the beginning of a year, Mr. Gomez saved 20,000 ringgit in his savings account with an interest rate of 4% per annum, and the interest is compounded once a year. Derive a mathematical model for Mr. Gomez's total saving after 3 years of saving. Solve this problem through mathematical modeling. The first step, identifying and defining the problem. Mr. Gomez is given compound interest which compounded once a year. His principal is 20,000 ringgit. The yearly interest rate is 4%. So we need to derive a mathematical model for Mr. Gomez's total savings at the end of 3 years. The second step, making assumptions and identifying the variables. We assume that Mr. Gomez did not withdraw or raise his savings throughout the period of saving. The variables are principal amount, RMP, yearly interest rate, R, number of times the interest is compounded, N, and time, T years. Step number 3, applying mathematics to solve problems. Keep in mind that when calculating the compound interest, each year we have 100% of the principal plus 4% of the previous balance. We construct a table as follows. This is the principal for 5 years. The interest received, principal plus interest, amount of savings. Step number 4, verifying and interpreting solutions in the context of the problem. Based on the table above, at the end of every year, the amount of savings is a power of 1.04 times the principal to 20,000 ringgit, and the power corresponds to the number of years of saving. We can generalize this pattern to a mathematical model by letting P represent the principal of the savings, T represent the number of years, and R represents the yearly interest rate. Hence, the mathematical model is AT equals to P 1 plus RT. Note that 1.04 equals to 1 plus 0.04 equals to 1 plus R, where AT is the amount of saving after 3 years. This mathematical model is an exponential function that allows us to calculate the amount of savings if the interest is compounded once a year for 3 years. This is a graph that shows an exponential function AT equals to 20,000 1.04t. The graph of the amount of saving after 3 years AT shows an exponential growth as the time t increases. Step number 5. Refining the mathematical model. The mathematical model AT equals to P1 plus RT is used for annual compounding. In reality, interest is often compounded more frequently. For example, compounded semi-annually or quarterly. If the interest is compounded monthly, the interest rate R is divided among the 12 months because 1/12 of the rate is applied each month. The variable t in the exponent is multiplied by 12 because the interest is calculated 12 times in a year. Hence, the mathematical model becomes AT equals to P1 plus R/12 powered by 12t. In general, if the interest is compounded n times per year, the mathematical model is AT equals to P1 plus R/n power of nt. The last step, reporting the findings. We can write a full report following the above modeling framework structure. This is all of my presentation. Thank you for watching.